Hello, can you guys hear me?
Yeah.
Great, thanks. Okay, so we are going to start with chapter 7. So this week we move into inferential statistics. So this is what we have been revving up for the past several chapters with all the sampling distributions and all that. We're going to use all that base knowledge to help us, infer about populations and start actually doing some statistical tests. So the past several chapters are probably a little harder because of the foundational knowledge that they contain, but I think you guys should do better from here on out. So we had to learn about the sampling distributions because that is where we draw our critical value, and we make determinations or inferences based on what we know from a sampling distribution. So as a result of this class, you will be able to understand the concept of a test hypothesis, provide a measure of reliability for our hypothesis test, which is called a significance level. We will test specific parameters, starting with means, proportions, and variances. Then we will show how to estimate the reliability of a test. So now we get to the elements of a statistical hypothesis test. So for example, let's say we have a population of interest, say JAU students. We form a hypothesis that on average, a JAU student spends $50 a week on coffee. Yeah, so they can pay attention in class. So we take a random sample from the population of JAU students. We find that the mean is actually only $20 a week. So we were not even close. So we reject the hypothesis that on average the JAU students pay $50 a week for coffee. That's kind of like the basis of hypothesis testing. We're going to get to the math part in a second. So, well, what exactly is a hypothesis? A statistical hypothesis is a statement about the numerical value of a population parameter. For example, I believe the mean GPA of this class is 3.5. That would be a hypothesis, right? It's something we can check. So the null hypothesis is denoted as H0, H null, H naught. That's what this stands for. And that represents the hypothesis that will be accepted unless the data provide convincing evidence that it is false. This usually represents the status quo or some claim about the population parameter that the researcher wants to test. This is also probably the answer to question 1 on your homework. So the alternative or research hypothesis is denoted as HA. It can also be denoted as H1. So the null was H0, so H1, I guess it kind of makes sense. Higher level classes, that's usually how it's denoted. So this represents a hypothesis that will be accepted only if the data provide convincing evidence of its truth. This usually represents the values of a population parameter for which the researcher wants to gather evidence to support. All right, so the alternative or research hypothesis is the opposite of the null hypothesis. And we never really accept the alternative hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis. Those are the only two outcomes that can occur from our hypothesis testing. We either reject the null or we fail to reject the null. So just some terminology you're going to need to know. So we designate the alternative hypothesis as HA. It can be set up in the form of not equal, less than, or greater than. So if it's a not equal, then it's a two-sided hypothesis. And if it's just a this inequality sign less than or greater than, it's a one-sided hypothesis and it's directional. Okay, let's do an example problem. So test that the population mean is not 3. So we want to test the hypothesis that the population mean is not 3. That is our alternative hypothesis. So HA is mu does not equal 3. And our null hypothesis is that mu does in fact equal 3. So mu does not equal 3, mu equals 3. So our alternative hypothesis will be HA does not equal, or HA is mu does not equal 3. And the null hypothesis will be H0, or H0, is mu equals 3. This is the first step in setting up a hypothesis test, is to identify what the hypothesis actually is. So, another example. Let's see, do Americans on average watch 12 hours of TV a day? So do they watch exactly 12 hours of TV every day? So the mean would be 12. So our alternative hypothesis would be that the mean TV viewing does not equal 12. And the null hypothesis would mean that it does equal 12. Whenever we're testing, the alternative will always be the not equals 1. And the null will always be the equals. Now, what it's kind of really saying, if we phrase the question a little differently, it might make a little more sense. So, see the different in italics here? Here we are asking if the viewing habits are different than 12 hours. But see how the alternative hypothesis is still a not equals hypothesis. So, okay, now let's move to a directional hypothesis. Is the average cost per hat less than or equal to $20? Statistically, the mean is less than or equal to 20. The only way to reject the hypothesis is if the average cost of a hat is greater than 20, right? So we are interested only if the average cost for that hat actually exceeds 20. So the alternative hypothesis is that mu is greater than 20. The null hypothesis is any value of 20 or less. So you can see HA colon mu is greater than 20. That's our alternative hypothesis. The null hypothesis, H0 colon mu is equal to 20, or it should be less than or equal to 20, because it's directional. We're really only concerned with this direction. So in Pearson, it could come up as equal or less than or equal. Generally, we're going to make it less than or equal. Okay, so is the average amount spent in the bookstore greater than 25? So this hypothesis flips the other direction. Now we want a greater than or equal null hypothesis, and the alternative or research hypothesis is when the mean is less than 25. You'll notice that with the alternative hypothesis, there is never an equal. It's always going to be a greater than or a less than, and only the null gets to have the equal or the less than and equal. Just some notes to pick up on. Okay, so in order to determine if we can actually reject or fail to reject the null hypothesis, we need something called a test statistic. The test statistic is a sample statistic computed from information provided in the sample that the researcher uses to decide between the null and alternative hypothesis. So the way inferential statistics works with test statistics is that we have a sampling distribution of our x bar, right? So I mean, sampling distribution, x bar, that would be our mean, right? And then distributed by so many standard deviations. So here we are assuming the population mean is 2,400. We want to know the chance of observing a mean 2,400 if in fact the true population mean is 2,400. So this is what our sampling distribution looks like. And we really never know what our population parameters are, right? That's why we're estimating. We're using inferences about it. So we want to know that with 95% confidence that the true mean is 2,400, or that there is less than a 5% chance that we are wrong. This is called alpha, which represents the rejection region in our sampling distribution. So this alpha 0.05, the shaded area, this represents the area that we're interested in order to reject the null hypothesis. So if we get a test statistic that is greater than 1.645, it will be in this area and we'll be able to reject the null hypothesis. So we're going to be interested in two types of error. A type 1 error occurs if the researcher rejects the null hypothesis in favor of the alternative hypothesis when, in fact, the null is true. The probability of committing a type 1 error is denoted by alpha. Basically, we want to minimize the percent chance that we falsely reject the null hypothesis. So the rejection region of a statistical test is the set of possible values of the test statistic for which the researcher will reject the null in favor of the alternative. So we want to find a z-score higher than the value we predetermined. Here it is 1.645 standard deviations from the mean, which is equivalent to a 95% confidence level for one-sided or one-tailed test, or an alpha of 0.05. Now, if we get a z-score higher than 1.645, then we can reject the null hypothesis. And in this example, we got a z-score of 2.12, which puts us in the rejection region, and thus we can reject the null hypothesis. So on the other side, we have a type 2 error. It occurs if the researcher accepts the null hypothesis when in fact null is false. So the probability of committing a type 2 error is denoted by beta. We don't tend to focus as much on beta as we do on alpha. Beta has to do more with the power of a test, which we'll get to later in this class. So if the null is true, and we fail to reject the null, then that is the correct decision, right? That puts us in this little table here. However, if the alternative was found to be true, but we fail to reject the null, then we commit a type 2 error, which is beta, right? If we reject the null and the null is true, then we commit a type 1 error. If we reject the null and the alternative is true, then we have made the correct decision. Elements of a test of hypothesis. The null hypothesis, noted as H0, is a theory about the specific values of one or more population parameters. The theory generally represents the status quo, which we adopt until it is proven false. The alternative or research hypothesis, HA, is a theory that contradicts that null hypothesis. The theory generally represents that which we will adopt only when sufficient evidence exists to establish its truth. So we never accept the alternative hypothesis until we get sufficient evidence to exist. But it's never going to be something we're going to do. So it's always going to be, we're going to reject the null, which would be symbolically accepting the alternative, but we're never going to say that because we're never going to have enough evidence to say that we can accept the alternative. So we're going to say we're going to reject the null. And then the other side is that as we fail to reject the null, so we don't say that we accept the null hypothesis because we really don't know. We have a statistical probability that we know, but it's never going to be perfect with all the other variables that could be occurring. So the test statistic is a sample statistic used to decide whether to reject the null hypothesis. The rejection region are the numerical values of the test statistic for which the null hypothesis will be rejected. The rejection region is chosen so that the probability is alpha that it will contain the test statistic when the null hypothesis is true, thereby leading to a type 1 error. The value of alpha is usually chosen to be very small, usually 0.01, 0.05, 0.10, and it is referred to as the level of significance of the test. So the assumptions are a clear statement of any assumptions made about the population being sampled. Remember, a moment ago I was saying how we don't have sufficient evidence to accept the alternative hypothesis. That's due to all the assumptions being made, and there's millions of more assumptions probably about a particular test that we don't know all the answers, so that's why we say we reject the null. Anyway, so experiment and calculation of test statistic. Performance of the sampling experiment and determination of the numerical value of that test statistic. Conclusion, if the numerical value of that test statistic falls in the rejection region, we reject the null hypothesis. I conclude that the alternative hypothesis is true, but like I said, we're never actually going to say it's true. We know that the hypothesis testing process will lead to this conclusion incorrectly, type 1 error only alpha percent of the time, and the null is true. So if the test statistic does not fall in the rejection region, we do not reject the null. Thus, we reserve judgment about which hypothesis is true. We do not conclude that the null hypothesis is true because we don't, in general, know the probability beta that our test procedure will lead to an incorrect acceptance of the null, or type 2 error. So we can test several population parameters. We're going to work on the mean, proportion, and variance. We'll do a couple examples in this class, and then on Wednesday we'll do some more examples. Okay. So next, we're going to formulate a hypothesis and set up the rejection region. So steps for selecting the null and alternative hypothesis or hypotheses. Select the alternative hypothesis as that which the sampling experiment is intended to establish. So the alternative hypothesis will assume one of three forms. So we have our sampling distribution, and we can be interested in one of three outcomes: the upper tail, the lower tail, or the area in both tails. So is the mean greater than 2400? That's the upper tail. Is the mean less than 2400? So that would be the lower tail on our distribution. And if the mean does not equal, then we are interested in both tails, right? We're going to split that alpha up into both tails for a two-tailed test. Then we're going to select the null hypothesis as the status quo, that which will be presumed true unless the sampling experiment conclusively establishes the alternative hypothesis. The null hypothesis will be specified as that parameter value closest to the alternative in a one-tailed test and as the complementary or only unspecified value in a two-tailed test. So a one-tailed test of a hypothesis is one in which the alternative hypothesis is directional and includes the symbol less than or greater than. Two-tailed test of hypothesis is one in which the alternative hypothesis does not specify departure from the null in a particular direction and is written with the symbol not equal. Right, so the basic idea is that it is unlikely that we would get a sample value so extreme that there is no way that the null hypothesis could be true. Therefore, we reject the null hypothesis. So back to our first example about the amount of money JU students spend on coffee in a week. The hypothesis was an average of 50. But what if we got a mean of 48? Is that difference enough to reject the null hypothesis? Probably not, right? Likely, it was just sampling error or some kind of bias in how we drew our sample to arrive at that mean. And thus, we cannot reject the null hypothesis of an average of $50 spent on coffee. But the more extreme that value is from our sample, the more extreme it is away from the average of 50, more likely that 50 is wrong, right? So is an average of 20 extreme enough to reject the null hypothesis? Well, I would have to use math and calculate z-scores out and stuff to actually determine that answer, but the rejection region does not include the critical value. We have our sampling distribution, and in a one-tailed test, if our test statistic falls within that rejection region, then we can reject the null hypothesis. Else, we fail to reject the null hypothesis. In a two-tailed test, we split the area of alpha into the two tails. So it is actually harder to reject the null hypothesis in a two-tailed test than a one-tailed test. Here, we do not care about the direction of the test. In the real world, most of our hypotheses will actually be set up like this. And most of the software will generate a two-tailed test, and then you'll have to kind of manipulate that to get the one-tailed version. But this, in the real world, is what most of hypothesis testing actually looks like. All right, so these are some common critical values you should remember. If alpha equals 0.1 in a one-tailed test, the critical value is 1.282. Very important number to remember. If it is a two-tailed test, then it will be equal to 1.645. Those are the critical values that we're going to be comparing our z-score from our sample to. You can see how hard it is to reject the null in a two-tailed test because the critical value is higher for the same level of significance. So if we have alpha at 0.10, which means we have a 90% confidence level in our result, and we get a 1.3, well, we can reject the null in a one-tailed test, but we would fail to reject the null in a two-tailed test, right? So that's why in research and in the real world, we tend to use two-tailed tests because we don't want to commit that type 1 error, right? Okay, so for alpha of 0.05 in a one-tailed test, the value is 1.645, and in a two-tailed test, it is 1.96. This is probably the most widely used alpha level, so definitely remember those numbers. 0.01, the critical value is 2.326 for a one-tailed and 2.575 for a two-tailed. All these values come from the normal distribution and represent the number of standard deviations of area under that normal curve. That's why we had to learn about the normal distribution in previous chapters and how to get z-scores, all building up so we could do this hypothesis testing. Okay, observed significance levels. Now we come to p-values. Most of the time, we are looking for a p-value of less than 0.05, where 0.05 is that alpha. So if we get a p-value that's less than that, and that means we can reject the null hypothesis. Okay, so what is a p-value? The observed significance level, or p-value, for a specific statistical test is the probability, assuming the null is true, of observing a value of that test statistic that is at least as contradictory to the null hypothesis and supportive of the alternative hypothesis as the actual one computed from sample data. So probability of obtaining a test statistic more extreme than actual sample value given the null is true. This is called the observed level of significance. The p-value is less than the alpha we set, and we can reject the null hypothesis. So p-value greater than or equal to alpha, do not reject the null. So if it's equal to 0.05, we can't reject the null. If it's 0.06, we can't reject the null. But if it is less than alpha, so let's say 0.04, then we can reject the null. Okay, steps for calculating the p-value of a test hypothesis. Determine the value of the test statistic z corresponding to the result of the sampling experiment. So if the test is one-tailed, the p-value is equal to the tail area beyond z in the same direction as the alternative hypothesis. Thus, if the alternative hypothesis is of the form greater than, the p-value is the area to the right or above the observed z-value. Conversely, if the alternative is of the form less than, the p-value is the area to the left or below the observed z-value. If the test is two-tailed, the p-value is equal to twice the tail area beyond the observed z-value in the direction of z negative, that is, if z is positive. So the p-value is twice the area to the right of or above the observed z-value. Conversely, if z is negative, the p-value is twice the area of the left or below the observed value. Basically, what we have to do is take our p-value and divide it by 2 because it represents the area in both tails. So choose the maximum value of alpha that you are willing to tolerate, usually 0.05. The observed significance level, p-value, of the test is less than the chosen value of alpha, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. Okay, so let's do an example how we calculate this out. So we have an average box of cereal contains 368 grams of cereal. So we take a random sample of 25 boxes that get an X-bar average of 372.5. The company has specified that there is a standard deviation of up to 15 grams. So we want to find the p-value and compare it to alpha 0.05. So alpha 0.05, that's our tolerance level. All right, so let's do this. So Excel's not perfect for one or single sample. We're gonna have to do some manipulation to make Excel work. Gosh, let's take this down. Okay. So what do we know? We know that our mu is 368. So that's our population mean. We take a sample, so n equals 25. We get our X bar is 372.5. Our standard deviation is 15. And we're going to need our variance. So if you remember, the variance is the standard deviation squared. Because we're using Excel, we're going to have to use a dummy variable, 0. And what else? Oh, alpha was 0.05. Okay, so that's all the things that we have to pull out of that problem so that we can make Excel do this. So it's not perfect, but it's kind of, how can we make Excel work in a way it wasn't intended to. So we know that we have sample 25 and that their average is 372.5. So what we can do is create a column of data of 25 of that mean. So if we add up all these numbers, 372.5, and then we divide by 25, we should still get 372.5, right? So we need an array of data to make this work. Right, so we can go to the Data tab, go to Data Analysis, and we're going to go to a z-test to sample for means. Wait, so remember how I said we only have one sample, right? So that's why we have to create this dummy variable. Okay, so variable 1 range, we're going to highlight our column for our sample mean. For variable 2 range, that is our dummy variable. Hypothesized mean difference, that is 368. Okay, variance, we know the variance because we just calculated it out, is 225. Now for the variance of our dummy variable, we want a super low number. So we're just going to put something super low. We have to have something there to make it run. It really has no bearing on us running the test, but we need it to work for it to run. Okay, so then output range, we're going to put it right here. Okay, so that's how you set up a 1 sample test for the means. We have to use the 2 sample because 1 sample doesn't exist in Excel. So we can delete this last column because that was just our dummy variable that we put there so that we can make Excel run. All right, so there we go. So we do a z-test, 2 sample for the means. The mean was 372.5. That's our sample mean, our X bar, right? We know the variance because we calculated it out from the standard deviation. We have 25 observations, so n equals 25. Our hypothesized mean was 368. So we get a z-score of 1.5. It's actually 1.499999. And then it's going to give us our p-values for both a one-tailed test and a two-tailed test. So if you remember, we were interested in a two-tailed z-test, right? So alpha is 0.05, and we got 0.13. If you remember, if our p-value is greater than alpha, then we fail to reject the null hypothesis. So in this instance, we had an HO for mu is equal to 368, and then our HA was mu. Go input a symbol, I think. Does not equal 368. So that's our hypothesis we're testing, right? And we got our p-value, so we failed to reject the null hypothesis. So that's this question. So if you wanted to do it manually, you can calculate out the z-score. by taking our x bar that we found, subtracting it from population mean mu, divide it by the standard deviation divided by the square root of n. So same way that we found z-scores before, we calculate that out. We then we know that for a two-tailed test, 0.05 was 1.96 roughly. So we know that 1.5 is less than 1.96, and thus we fail to reject the null hypothesis because this, our critical value is not in our rejection region. So it shows you how to calculate out the p-value, subtracting the area between 0 and 1.5 and our actual value. Okay, so that's that. So do not reject the null because we did not get a critical value high enough, or test statistic was higher than our critical value. Oh yeah, so let's do another example. Well, actually, we've already done this example because Excel calculates out our one-tailed forest, 0.06. So we set it up the exact same way. It gives us 0.06 for one-tailed, and it's still not, the p-value is still too high to reject the null hypothesis. So based on a one-tailed z-test, we still fail to reject the null. Okay, one-tailed z-test, calculate out our z-value the same way. Calculate out our p-value, and so same concept. We needed higher test statistic. The z-value needed to be higher than 1.645 in this case, and it was not. So our p-value is 0.06, which is higher than 0.05. Thus, we do not reject the null. Right, so let's do a second example. You're an analyst for Ford. You want to find out if the average miles per gallon of Ford Escorts, is less than 32 miles per gallon. Similar models have a standard deviation of 3.8 miles per gallon. We take a sample of 60 Ford Escorts and compute the sample mean 30.7. What is the p-value? How does it compare to an alpha equals 0.01? Let's set this one up. New sheet. Okay, so we have a sample size, this off to the side, of 60, right? We're going to take this all the way down to 60. All right, I'm going to go back up to the top. All right, so pull what we need from it. We have a mu equal to 32. Standard deviation was 3.8. Our variance is our standard deviation squared. Sample size 60. Our x bar 3.7. We have an alpha 0.01, and we have a dummy of 0. All right, so that's everything we need to run our hypothesis test. So our H null, H0, is that mu equals 32. Mu equals 32. HA, mu, let's go steal this symbol. Alright, so null hypothesis, mu equals 32. Alternative, research hypothesis, mu does not equal 32. Well, actually, it is going to be, this was a one-tailed, right? Less than. So it means our alternative should be greater than, right? It should be less than or equal. So mu is less than or equal to 32. Wait, it's the other way. You want to find out if the average miles per gallon of escorts is less than 32. Similar models have taken, so it's the other way. I want to know that's less than, so course Ford would like to believe that their escort has a mu greater than or equal to 32. So that's the hypothesis for testing. We are going to go back to the data analysis, do sample means. Okay, so we're going to capture our data, A1 to A60, dummy variable, hypothesized mean is 32. Our variance is 14.44. Super small number for the variance. Now we're going to change this to 0.01. I'll put our answer there. Okay. So, don't need this. Move this all over. Okay. So, our actual mean from our sample is 30.7. Variance is 14.4. It's 60 observations. Our hypothesized mean is 32. We got a p-value of 0.003, which is less than 0.01. Thus, we can reject the null hypothesis that the mu is greater than or equal to 32. So they did some rounding, but they calculate out the z-value. We know that it is less than, and our value was okay. So if we want to convert a two-tailed p-value from a printout to a one-tailed, if it is one-tailed, it's the reported p-value divided by 2, right? Because we've stuck all the area in one tail, and now we're dividing it to 2. If we have the other side of the other side of the distribution, then we do 1 minus that value. So z is positive or z is negative based on that direction. Okay, so we'll finish chapter 7 on Wednesday, and I'll go over some more examples and questions for the test and whatnot on Wednesday. So see you guys then. Thanks everybody for coming. You have a good day too.